estimates of gas and dust that we have for CANDELS galaxies. And I'd like to highlight in particular, how's that? I'd like to highlight in particular the work of Lin Lin, who was a visiting postdoctoral scholar with us at Santa Cruz from Shanghai Observatory for the better part of a year. So here's the plan of my talk. We're going to estimate gas contents from 2 different star formation laws, and we're going to use those to compute an average galaxy average tau along the line of sight, correcting for metallicities as a function of time. I'm going to compare those to the observed absorption values, AV, which are gotten from spectral energy distribution fitting. And we're going to find that the tau values are a lot higher than the AV values, but that there's a nice model in the literature which can account for this, assuming that the dust is in very clumpy clouds. So that's a précis. Moving forward, we'll be using 3 star formation laws in total. One is for molecular gas, and the star formation rate is linearly proportioned to that. Here we're using beautiful work by Reinhard Genzel and his team. And then there are 2 star formation laws based on total gas content, H1 plus H2. And one of them is the traditional Schmidt-Kennicutt law, which just says that star formation rate is proportional to the gas power to a positive power greater than 1, 1.4. And the other is called the extended Schmidt-Kennicutt law, which has a linear term in gas here, but an additional term due to stellar surface density in an attempt to take into account the fact that gas at higher pressure has a higher molecular hydrogen content. We'll use both of those, SK and ESK. So here are some first results. We use the measured star formation rates from SED fitting to derive H2, the molecular content, and the total gas using the Schmidt-Kennicutt law. So the molecular gas is in blue here. And let me, just before I delve into the details, explain the format of the plot. Each one of these panels is a plot of gas content in solar masses versus this parameter, which is a measure of galaxy radius, relative radius compared to the average of galaxies in that bin. And these are bins of mass going this way and redshift going this way. So we're getting up to redshift 2.5 here. Our minimum redshift is 0.5. We go from 9.0 in the log to 11.0 in the log with mass. So the blue points are the molecular hydrogen content, and you'll note that they are flat. Let me move on so you can see the point. There you go. The blue points are flat, and that is because there's no trend in star formation rate as a function of galaxy size in the CANDELS galaxies. And since the logarithm is 1.0 in the molecular law, that means that there's no trend in molecular gas either. So that accounts for the fact that the blue points are basically horizontal. And then there's the black points. The black points are the total gas content from Schmidt-Kennicutt. And you'll observe that they are inclined. And the reason for that is that you have to put more gas into a big galaxy because it's less efficient because of that 1.4 power in the exponent. So we compute the black points and the blue points, and then we subtract to get the neutral hydrogen points, which are the red points. Let's move forward to the next slide, which is the same basic slide, except instead of using Schmidt-Kennicutt, we're going to use the extended Schmidt-Kennicutt law. Okay? So I'll bounce back and forth a few times so that you can compare. Basically very similar. So here are the conclusions from these 2 slides. First, as I've noted, the mass of the molecular gas is constant with galaxy radius, whereas the mass of the H1 increases with galaxy radius. At low mass, the gas is mostly H1. At high mass, it's mostly H2. There's not much of a trend in these panels with time, from Z of 2.5 to 0.5, and total gas masses are slightly larger with ESK, but generally the trends are basically the same. Okay, so now we have gas mass estimates for our galaxies. Let's now turn to the absorption measurements. These are measurements of AV from spectral energy distribution fitting. And again, I'm going to show these in panels. And each panel is AV, the log of AV. Actually, it's the log of the magnitude. And this is delta log radius. So again, this is galaxy size here. And we're only using face-on galaxies to avoid the complication of what AV does at high inclination. So imagine that you're just looking at round objects here. And the data are shown by the red points. Well, first of all, the data are shown by all of these points, and then take median points to get red points, and then put a line through them to get a red line. So the red line is the least squares slope of the observed points. And then, to compare, there are some model lines. And I want to highlight particularly these two. The solid one is the ESK line, and the dashed one, this one here, the big dash, is the line from Schmidt-Kennicott. And so those predictions, the AV predictions, are assuming that AV is proportional to the gas column density, adjusted for changing metallicity of the ISM back in the past. So the thing that you notice in this panel, and you'll see it in all of the panels in just a second, is the fact that the data have a modest slope, whereas the models on average have steeper slope. In this particular graph, ESK agrees pretty well with the data, but Schmidt-Kennicott is too steep. So in words, if the line is too steep, what we are is we're predicting that the smaller size of these galaxies is giving them a higher surface density of gas and therefore a higher surface density of AV. Okay, well now let's see what this looks like as we go forward in the same kind of plot that we had before. I'll focus your attention first on this panel, which is the one that we were just looking at. And you can run your eye down this column of little galaxies back in time and see how the situation has changed as we go back in time. And the main thing that you see with regard to the data is that the line is shallow here. The red line is horizontal, whereas it was somewhat inclined when we looked at the more recent galaxies. And that's true in all of these mass bins. In general, the slopes of the data are lower early in time. And then in addition, you can run your eye this way, and you can see that the average value of the absorption is increasing with galaxy mass. The colors don't mean very much because what we've done is we've only used face-on galaxies. So those colors of the individual points are the B over A ratio, but everybody is bigger than 0.5. So as you peruse these results, you can see one of my major conclusions, our major conclusions, is that it's systematic. So the slopes are varying systematically and the 0 points are varying systematically as a function of time. So even yes, there's noise in the data, nevertheless, there is definitely systematic trends. Okay, so let's move on and reach some conclusions here. First is that the absorption increases with galaxy mass roughly by 0.4 decs from here to here. AV increases with time, roughly 0.2 decs, not so much. Small galaxies have more AV at low Z, but less AV at high Z. That's the red slopes of the red lines. And in general, the ESK fits better than the SK, but the observed trend in AV scales with size is always less, in general, on average, than the gas masses predict. So that was the phenomenon that got our attention in the first place, the fact that you could make guesstimates of how much AV would change, and it wasn't changing that much. But when we dug into it a little bit deeper, it got worse because, which I'll show you in the next plot, okay? So again, the same sort of format. Here is the predicted logarithm of AV versus galaxy size. Keep your eye on the black points. I apologize that they're in the background, but that's what you should be focusing on. The black points are total gas, and they would go with total AV. So, looks good. The black points are in general located at the level of the red line. The red line is the data from the previous slide, and that's true throughout. But the point is that that's a fudge because we have applied corrections which are given up here in DEX in order to move the black points down to agree with the red lines on average. And those corrections are big. They range from minus half a DEX here to a whole DEX. So that expresses the fact that overall, never mind slopes and differential things, but overall, there's a lot less absorption in these galaxies than you would have predicted from their gas content. These are the numbers for Schmidt-Kennicott, and the next slide shows you the numbers for extended Schmidt-Kennicott, which are actually even slightly bigger and average more like 1 DEX on average. Okay, so we were, yes? Pardon? Nothing. We've just, to this point, we've assumed it's uniform over the face of the galaxy. Is that your question, distribution? Correct. Filling the exact same area as the light. That's right, in a uniform way. So it is well known that effective absorption can be very much influenced by the spatial distribution of the dust, which is coming to Peter's point here. In particular, you can have a fixed amount of dust and make it less effective if you put it into clumps, because then most of the lines of sight are clear or clearer. So we were playing with some models like that when we discovered this paper by Sion and Drain in the literature, and it was a gift from heaven. It was exactly what we needed. So this is a paper on clumpy dust models of in which the distribution of gas, the spatial distribution of the gas density, is modeled using a Kolmogorov turbulence law, parametrized by the Mach number, m sub s. So here's a picture from this paper. Here are Mach number 1 distributions, and here are Mach number 12 distributions. And it looks like there's less total gas here than there, but that's not true. It's just that all the gas is squished up into the clumps, and so it doesn't appear as a more uniform distribution. Okay, so let's see how well this model actually fits our data, does it? Let's explain the form of the model data that they give you. They give you a whole series of panels that looks like this. Each panel is AV in magnitude, and then this is the average tau from the gas column. So this average tau is the tau that you get by taking all the gas and dust in particular, and making it uniform across the face of the galaxy. Tau is optical depth, right. So the relationship between tau v and AV is very close. If you have a tau v and at low values of the absorption, then AV is about 10% bigger in number than tau. So if you have a tau of 1, then your AV is going to be of order 1.1 magnitudes. Okay, so that is obeyed by small slopes with small values of the absorption, but in their models, when you have high tau, this is an optical depth of 20, huge, if we had all of that gas uniformly spread out over the galaxy. we can have situations in which the effective AV is more like 1.2 magnitudes, which is right here, okay? And this applies, the red curves apply to models with a Mach number of 20. And what we're doing here in the models is varying this quantity, R sub S over R sub D. What is that? Their model geometrically is simple. It involves only spheres, and there is a sphere of stars, R sub S, and a sphere of dust, R sub D. And so if R sub S of R of D is 1, those two spheres are the same size, and the dust is uniformly mixed with the stars. If, for example, R sub S over RD is 0.6, it says that the sphere of stars is 0.6 as large as the sphere of dust, so that a lot of the dust is outside of the stars. Okay, so the point of this slide is to illustrate that for their models at high Mach number, there can be a huge discrepancy between the average tau and the average effective AV. So we took those models at Mach 20 and plotted them versus our relationship, because we have AV and we have the average, spatially average tau. And here are the results. Okay, so the red lines are their models with various values of this ratio R sub S over R sub D. The data are the logarithm of our AV versus the logarithm of the tau. This is for gas masses and AV estimated from Schmidt-Kennicott. The next slide shows you estimates from extended Schmidt-Kennicott, which fits a little bit better. But the models really actually fit the points surprisingly well in two ways. First of all, they have relieved the offset. Now the points more or less lie on top of the line. And they also match the slopes quite nicely. Remember, we were finding slopes in the data that were smaller than predicted, and now that's nicely explained by these models. There are still some discrepancies at low mass and early times. Okay, so overall, this is a nice fit.
So can we say the color code is the size of the galaxy?
Yes, this is as before, the relative radius of the galaxy, what I've been calling galaxy size. So these are the little galaxies, those are the big galaxies. Thank you, Joel. Okay. So nice match between tau and AV using the models. Not so nice match when we actually try to predict the Calset Law, because the absorptions that have been derived from SED fitting by CANDELS in the CANDELS catalog generally assume the Calset Law, most of them. Focus on this panel here. This is R sub S over RD equals unity, and a Mach number of 20, which is what we prefer. The Calset Law and its uncertainties is shown by these black lines, 3 black lines. And our favorite model is this one. And you can see the model is a lot grayer as a function of wavelength than the actual Calset Law, which has been used in order to find AV. So that's a lingering issue that needs to be looked into further. Okay, I will now summarize. The main point is that the total tau in distant galaxies seems to be bigger than you would think from AV. And if in fact tau is 20, that would, in big galaxies, that would convert to an absorption of 22 magnitudes on average if the dust were uniformly spread out. You wouldn't be able to see anything, right? So this is due to the fact that the dust is very clumpy and lines of sight with low tau dominate the light. These models by Sion and Drain match this rather nicely. And incidentally, you might wonder, well, is Mach number equal 20 a reasonable number? And there's one paper by Federath et al. In which they have schematically measured that from H alpha line widths, and they come up with values in between 20 and 80. So we can have a discussion about whether these things are physically reasonable. Remember, really what counts is the clumpiness, not the Mach number. So I think this kind of raises questions as to what we're actually modeling in these galaxies. The Calset Law is not quite uniform from object to object, but it's remarkably uniform, and yet these models suggest that by making small tweaks in the clumpiness, you could get big differences. And I'm concerned that the data seem to be well fitted in one respect, AV versus tau V, but not so well in terms of the overall slope of the Calset Law. So I'm just wondering, gosh, do we have a very fragile situation in principle, and how in practice does it look so nice as it actually turns out? Three smaller points. The trend in AV versus galaxy radius is slightly better fit by ESK than SK. All the trends, regardless of any model, are systematic as a function of mass and time. And a point that I didn't make before, but I'll introduce it at this time, is the fact that we saw a change in slope in AV versus galaxy size, in the sense that at early times that was flat, at late times it was steep. We've also, in parallel, been doing a study of galaxy shapes, and we think at early types at those low masses, we go from prolate galaxies to disky galaxies, and maybe this change of slope here that we're seeing relates somehow to a change in the overall shape of the stellar distribution from prolate at early times to disky at late times. And I'll close there.
Questions? Yeah.
Hello. Okay, sorry. Okay, Sandra, thank you very much for this very nice talk. So I was wondering, the dust clumpiness, I mean, as you call it, it's not entirely clear what that means. I mean, I think it means non-uniform for sure.
Yeah, for sure. Yeah.
Is there any way how you could find out observationally is whether it's like a really kind of like small dust clumps, or whether it's just like star-forming regions that have kind of blown out their surroundings, and that's what you see? And is there a way to find out, to distinguish these different good scenarios?
I think there would be at low redshift. I don't think there's much of a chance of this with our current resolutions in CANDELS. But the Federath group, the Federath group have published a couple of papers looking at clumpiness of local distributions, mainly molecular clouds. They also included the SMC, and more recently, a few other very nearby galaxies. And they claim that this kind of clumpy distribution is consistent with nearby data.
Well, thank you, Sandy. Of course, this discussion reminds me of long gone times when the UV community and the infrared community would meet and discuss M82. This is now, so to speak, the continuation at high redshift. So, Robert, I mean, we call that birth cloud, okay? The birth cloud effect. And for the infrareders, it's very clear that the ISM is very clumpy. But my suggestion, Sandy, for the Calset Law is as follows. Could it be, since Calset laws, so that would be the UV part of the extinction, very much was invented in the local universe, where the optical depth effects, I mean, the taus are not so large. And where then, if you get into this regime of high extinctions in tau, that comes from nuclear regions. I mean, M82 would be the example. You look at it as in UV, you only see the outskirts, and that would then show a full bump, while the inner parts, which have the large tau, are separated, and you just don't see it in the UV. While at high redshift, of course, we don't yet have that kind of a spectral dependence. Maybe it is flatter, and that's where the analog to the local universe is not quite right.
Well, I certainly agree with you that I, at least, am going to return to the colors of galaxies as a function of mass and distance, you know, looking for trends versus wavelength or star formation rate or whatever. But I will say that a first cursory look, Reinhardt, indicates, paradoxically, that the Calset Law does a remarkably wonderful job for all galaxies of all masses at all redshifts covered by my graph. Now, there may be departures, and in fact, Brett Salmon found some small departures in his thesis, but thus far, it's going to be looking for, I think, small effects, not big ones. So this has me deeply puzzled.
Sandy, great talk. I was just wondering if you have clumpy dust versus not clumpy dust, shouldn't you see a different transition between face-on and edge-on AV? And if so, have you looked for that?
Well, we've certainly seen higher absorption in edge-on galaxies. Many people have seen that. But we've not had a chance to actually model it yet. So I really can't say, but it's another good thing to look at.
Hi, I like the talk very much. So my question is that, first of all, like, I would say like the attenuation law is more, well, because we know that most of the UV emission actually originates from the young star forming regions. So it's actually the problem on the small scale, like how those young star forming regions is obscured by the dust.
Completely.
Yes.
Totally agree with that. Yeah.
Yes. So, so I'm not sure, like using like such a spherical symmetric distribution model, how well it.
This is
works.
my great white hope
Yes.
that will solve the problem.
Yes. And the second thing is that I'm very interested in that simulation on small scale. And the problem is that changing the Mach number not only changes the clumpiness of the dust distribution, but also might change IMF. And when you do the SED fitting, actually the IMF will impact the AV that you derived. And basically there are a lot of things that, I'm saying that there might be like multiple factors that are like coupling with each other. So you have to like find ways to like decouple different factors.
So let's move to the next speaker. Well, let's thank Sandy again.